Let's jump right into it. Today's explainer is about a truly incredible journey. We're tracking the path of a Nobel laureate who started out treating patients in a clinic, moved on to literally mapping the complex wiring of the human brain, and is now tackling the absolute cutting edge of the AI revolution in biology. It's a massive shift. It's a story about that deep, restless drive to solve the unsolvable, and how the tools we use to understand life itself are radically changing right before our eyes. Okay, let's dive into our roadmap for this. We'll start with a wild career pivot from musician to scientist, then get into mastering the brain's synapses. After that, we'll look at the gritty reality of scientific discovery, and finally, tackle the massive collision of AI, biological data, and the real challenges threatening future innovation. Section 1. From musician to scientist. A pretty surprising journey. So, our subject today is a German immigrant who spent over 40 years in the US, ultimately becoming a hugely influential researcher at Stanford University. But get this, his path to the absolute pinnacle of science was, well, it was anything but straight. He actually started out wanting to play classical music in an orchestra, but he admits he just kind of lacked the talent. So, scratch that. He pivots to medicine. But as a practicing physician, he hits this harsh reality. He felt completely powerless to actually help his patients because the underlying science for their diseases simply wasn't there yet. And it was exactly that immense frustration that drove him away from the clinical bedside and into the research lab, first studying cholesterol and eventually becoming a neuroscientist completely focused on how the brain communicates. This profound feeling of helplessness as a clinician, that was the absolute catalyst for his entire scientific career. He noted that, quote, physicians actually had very little power in helping patients. There was a lot of suffering because the science just wasn't there, end quote. He essentially realized that to truly save lives, he had to go all the way back to the foundational building blocks of human biology and find those missing answers himself. Section 2. Mastering the brain's synapses. Let's talk about cellular communication. Having made the leap from general medicine into neuroscience, he locked on to the brain's most fundamental mystery, synaptic transmission. So this is that essential process where nerve cells, or neurons, communicate with each other at these tiny contact points called synapses. They transfer and process information, basically forming the foundation for literally everything the brain does. And understanding this mechanism is absolutely crucial, because when synaptic transmission goes sideways, it contributes to almost every single disease of the brain. To really put into perspective why mapping this matters, just look at how synapses fail in totally different ways depending on the disease. In conditions like schizophrenia, for instance, the synapses might actually still work, but the wrong nerve cells are talking to each other in these abnormal, inappropriate ways. Now, contrast that with Alzheimer's disease. Their synaptic transmission becomes completely obliterated, starting in the hippocampus and just erasing memory. Grounding this abstract neuroscience in such tangible human stakes, well, it shows exactly why mapping these pathways is so vital for developing future therapies. Section 3. Reality of scientific discovery. It's an incremental grind. We really need to rethink how breakthroughs in this field actually happen. Because, the public perception of that sudden eureka moment, it's largely a myth. Discovery is a grind. Step 1 is carefully formulating a question. Step 2 is trying things in the lab, accepting the harsh reality that most of these attempts will lead to absolutely nothing. It's frustrating, it's a waste of time, but it's a necessary one. And then step 3 is incrementally building on those rare moments when something finally clicks. You can't just command scientists to discover a cure, because true discovery relies on wandering into the unknown. There's a quote from him that captures this perfectly. It is never one thing, boom. It is more like walking up a flight of stairs where each step counts. He even points out that his own Nobel Prize wasn't for some sudden stroke of solitary genius. Actually, it was just a wonderful recognition of incremental collective work built step by step alongside so many others who totally deserved the honor too. Section 4. AI and the Data Deluge. Welcome to the biological revolution. Fast forward to today and that painstaking incremental biology of the past, it's undergoing a massive revolution. Biology today is armed with tools that frankly sound like science fiction. We've got transcriptomics mapping entire gene expressions, CRISPR allowing us to literally edit genes, and cryo-EM letting us view the precise 3D shapes of molecules. And of course, the elephant in the room, AI. Specifically tools like DeepMind's AlphaFold, which he praises as a fantastic, highly productive use of AI that's giving us incredibly concrete biological knowledge about protein structures. But here is where we hit a massive roadblock. Just look at the stark contrast in our current reality. On one hand, the sheer quantity of biological data is enormous. We are literally drowning in thousands of descriptive papers and massive data sets. But the actual utility of all that data? Highly questionable. Companies are engaging in what's called AI washing, basically using the buzzword of AI more to impress their investors than to achieve any material scientific advances. And because so much biological data isn't standardized, feeding this enormous but low-quality data into an AI just results in classic garbage in, garbage out. We have an unprecedented abundance of data, but without proper standardization, it's practically useless for AI.
Section 5, the data quality moonshot, the biggest impediment we face.
This glaring contrast between sheer volume and actual usefulness leads to what this Nobel Laureate believes is our most desperate need right now. As he puts it, for me and science, a moonshot in AI would be extracting a judgment of the quality of data. Think about that. While a few specialized fields have parameters to check quality, the vast majority of scientific papers and data totally lack this. So the greatest impediment to AI in biology right now isn't the AI models themselves. It's the fact that we have no automated way to look at a million scientific papers and tell the algorithm which ones are actually true, well-researched science and which ones are just flawed.
Section 6, challenges to future innovation, navigating the hurdles ahead. Now, looking at the bigger picture, as an immigrant who deeply values the American dream, the researcher notes several stated concerns regarding the current climate for innovation. He views the curtailing of international scientific exchange and immigration as a severe detriment to discovery. Furthermore, he points to increasing bureaucracy, growing restrictions on free speech, and the need to protect constitutional rights from monetary influence as major hurdles. In his view, a healthy scientific ecosystem absolutely requires the free exchange of ideas and talent across borders.
Navigating all these challenges requires serious discipline, especially for young innovators just entering the field. He shares some incredibly direct advice he got from his own mentors, the scientific giants Mike Brown and Joe Goldstein. First, find a mentor who will actually tell you when you are wrong. Praise is nice, sure, but correction is essential. Second, choose goals that are aspirational but actually feasible. Dreaming up impossible goals just leads to failure. And finally, focus intensely. It is so easy to get distracted by 1,000 interesting things, but true breakthroughs require deep, narrow focus. And that intense focus brings us full circle. All of this, the journey from the clinic, the mapping of the synapses, the managing of the AI data deluge, it all matters for one ultimate reason. The profound hope is to apply these revolutionary new technologies to finally crack intractable, devastating diseases like Alzheimer's and severe cancers of the pancreas, colon, lung, and brain. This is the ultimate goal, fulfilling the clinician's original quest to cure the suffering that current science just cannot touch yet. So I want to leave you with this final, vital question to ponder. As AI begins to process millions of biological data points and scientific papers in the search for these life-saving cures, who decides what data is gold and what is garbage? The answer to that question will likely determine the success or failure of the next great era in medicine. Thank you for joining me for this explainer, and keep questioning the data that shapes our future.